Hi there. Today what we're going to be doing is looking at, continuing to look at parametric equations. And we're going to start by being given two sets of the parametric equations, and we're going to eliminate the parameter and write the corresponding rectangular equation. And so to do that, when we're given parametric equations, we'll start by solving for t in one equation. That's going to be our step one. Step two is that we're going to substitute that into the second equation. And what you'll see is that sometimes we'll have to go back and use some friendly faces from earlier. And then step three is just to have that final rectangular equation. Okay, so again, when we do this, we want to try, when we isolate t, we want to try to avoid any time that there's a plus or minus. So in example one, I would need to take the sixth root of x, which would have a plus or minus. So I'm going to isolate y here instead in step one, or isolate t here in the y equation. So to do that, I'm going to take y over 6 equals the natural log of t. And then if I want to isolate t, basically I need to rewrite in this in exponential form, since this is a log form. So remember that the natural log is like log base e. So I'm going to rewrite this as e is my base to the y over 6 is my exponent equals t. And so that's my step one. Okay. Now in step two, because I didn't use this x equation, in step two, now I'm going to actually put that in for t. So x equals t to the 6th, and I just found that t was e to the y over 6. Okay. And basically now I simplify that. And if I simplify, I can see that I'll multiply these exponents together, and I get x equals e to the y. Now, one thing is that it looks like we're done, but let's always write in terms of y whenever possible. So since y is in the exponent, now we're going to go from exponential to logarithmic form. So this is going to be log base e of x equals y. But we don't write log base e, we would write the natural log of x equals y. So that would be our rectangular equation. So I'll write it, it's a little prettier here. Y equals the natural log of x. Okay. Now number two, we see something a little bit different, but I'm going to show you a little trick for this. In number two, if we try to isolate t, we're going to end up with a hot mess here, aren't we? So what I'd like us to do is instead, when we have these trigonometric equations, let's just isolate the trigonometric part in both of them. Trust me for this one, okay? So if I do that for this equation for x, I would add 3 and then divide by 5. So I would get x plus 3 over 5 equals the secant of 2t. Now let's do the same thing here. I'd have to subtract 2, divide by 4. So y minus 2 over 4 equals the tangent of 2t. Now you may be saying, Mrs. Mackey, how does that help us? Well, I want us to think back to our friends, the Pythagorean identities. I know they're not going anywhere. So when we think about that, isn't there a Pythagorean identity that's involved with tangent and secant? So let's just recall our friend, the Pythagorean identity that says that tangent square theta plus 1 equals secant square theta. And let's put these pieces into this Pythagorean identity. So we're not really substituting in the second equation because we have two equations. We're going to substitute this into the Pythagorean identity. So we're going to take tangent of theta squared plus 1 equals the secant theta squared. And our tangent of theta, which in this case is 2t, is going to be y minus 2 over 4. And the secant of theta, which so secant of 2t is going to be x plus 3 over 5. And so if we look at this, this kind of looks like some of the conic equations that we've been dealing with, doesn't it? So what we could do is move the y squared term over. And what you might see is that this looks very similar to a hyperbola equation, doesn't it? So let's write this so it looks more like our friend, the hyperbola. So I'm going to write this as the quantity x plus 3 squared over 25 minus the quantity y minus 2 squared over 16 equals 1. And again, this is just a familiar equation. And so we want to write our equation in like a familiar form. And so we would write it in the standard form of the hyperbola. So that's kind of fun that these parametric equations that involve the trig functions end up giving us this hyperbola. So let's use that same thought process in number 3. So I'm going to isolate the cosine of 2t and the sine of 2t. And this doesn't have to be 2t. This could be like anything as long as they match. So let's use that idea again. So the cosine of 2t is x over 2. And then the sine of 2t would be y minus 4 over 3. Okay, so again, notice that we have sine and cosine, and that those two are also involved in one of our trig identities. That sine square theta plus cosine square theta equals 1. Okay, so let's do that. Let's put these into that Pythagorean identity. So for sine of theta, so sine of 2t is y minus 4 over 3. And cosine of theta is going to be the cosine of 2t, which is x over 2. And now hopefully you're seeing that this is looking like an ellipse. And I don't know, I mean, you could, addition is commutative, but usually we did write the x in the first term of the ellipse. So I'll just hold true to what we were doing and do that. And then we would have y minus 4 squared over 9 equals 1. And so there's our step 3, is to put it in a rectangular equation where it's familiar to us. And so since this is an ellipse, we'll use that standard form. Okay. All right, so another one like this is going to be number 4. We have x equals 1 over the square root of t plus 1 and y equals t over t plus 1. Well, this one has 2 t's in it. That's going to be a little maybe problematic to solve for t. So I'll choose this first one. And so in order to solve for t, I'm going to have to square to get rid of the square root. So I'll have x squared equals 1 squared, which is 1, over t plus 1. So basically, I just squared both sides of that equation. So x squared times t plus 1 equals 1. Still, we're working on isolating t. So t plus 1 equals 1 over x squared. And so t equals 1 over x squared minus 1. Okay, so I have my t. So now I'm going to substitute that into the other equation. So I'm going to take the y equation, and I'm going to have y equals t over t plus 1. Remember, my t was 1 over x squared minus 1. Okay. All right, so we can see this minus 1 plus 1 cancel out here. So I have 1 over x squared minus 1. These cancel. 1 over x squared. And so to simplify that, I'll multiply by x squared over x squared to get rid of that complex fraction. So that gives me 1 minus x squared over 1. And again, this was all y equals. And that looks pretty good to me. So y is going to equal negative x squared plus 1. I'll write it in standard form like that. Okay, and there you have it. All right, so that's a little bit about how we can rewrite the parametric equations in a rectangular form, and also use some of those Pythagorean identities to help along the way. Okay, all right, so the next part that we're going to look at here is when we have two different sets of parametric equations that end up, well, even more than two sets, that end up having the same rectangular equation, but they don't end up with the same plane curve. And so if we look at this, if we try to see what each of these is in a rectangular form, here we, in example 5a, it says that x equals t and y equals negative t plus 2. So if I just make t equal x, then I can put that in here and I get that y equals negative x plus 2. Okay. I could do the same thing here and I get that y equals negative x plus 2. And I can do the same thing here and I get that y equals negative x plus 2. So they have the same rectangular equation, but they're going to differ a little bit because of the restrictions on the original functions. Basically what happens is that we have to think about, in this case, because we're substituting the whole thing in for t here, that whole x variable, it turns out that the range of the x equals equation then becomes the domain of the y equals equation. Okay. So again, because that's our output, that's now becoming the input of the other one. That's why the range of the x equals equation becomes the domain of the y equals equation. So if we look here, when I think about the domain of the x equals equation, so the domain, like anything, can be t. So that means that x can be anything, all right? So our range here is anything negative infinity to infinity. So that therefore means that the domain of this function is negative infinity to infinity. And therefore now I can have anything that I have here for x. And so then my range ends up being negative infinity to infinity. Okay. So if we think about letter B, for example, instead, when we think about the range of this equation, remember that the range would be all the values of x that could happen when we have cosine theta. So remember that cosine theta only goes from -1 to 1. And so that now means that this is the domain that comes in here. So now that means that this can only be from -1 to 1. And so that means that this part, the x, is now only -1 to 1. So if we wanted to find the range, what we could do is we could find what it is at -1. So y equals -1 plus 2. So that gives me 3. At +1, that would be -1 plus 2, which is 1. So then just if we think about from lowest to highest, my range here would just be from 1 to 3. And if I look at this set of equations, when I think about e to the t, remember that e to the t, this exponential equation, is going to have a range of 0 to infinity, which now means that that's the domain of this function. And so now I can only go from 0 to infinity. So once again, you could see what happens when it's 0. So y would be -0 plus 2, which would be 2. And then I know we can't really substitute in infinity, but if we did, negative infinity plus 2, basically that's going to approach, I'm not going to say it equals, but it's going to approach negative infinity. And so then if we think about lowest to highest, that means that our range here would be from negative infinity to 2. Okay. So again, if we eliminate the parameter in all three sets, they do have the same rectangular equation, but they're going to differ in the domain and range and the orientation of the plane curve. So let's make a t-table to graph each of these, and then we can kind of see how that ends up differing and like kind of how this comes into play visually. It's kind of cool to see it play out. So I'm going to look at the first two equations here. And so if I'm going to make a t-table for those, so I'm going to have my txy table here. And again, I'll just go from -2 to 2. That could make sense. Oh, you have to see this, sorry. So I'm going to go from -2 to 2. And so again, remember here that x was equal to t and y was -t plus 2. So x is going to be equal to t in all of these cases. And then y is going to be equal to the opposite of t plus 2. So that's +2 plus 2 is 4, +1 plus 2 is 3, 0 plus 2 is 2, -1 plus 2 is 1, -2 plus 2 is 0, and we could plot those specific points. So we could plot -2, 4, -1, 3, 0, 2, 1, 1, and 2, 0. And we can see that we have an equation that looks like this idea of -x plus 2, which is there. And we want to include the orientation, and we can see that we're going in this direction. But the plane curve never really stops. Remember that this could be any value. So this is going to keep continuing in all of those directions. So I'm going to put those little arrowheads on both sides to imply that it's going to keep going and going and going. Okay. If we were to do the same thing with this next set, remember that in this set, x was cosine of theta, and that y was the opposite of cosine of theta plus 2. So if we were to make our t-table here, it might, instead of a t-table, because our input was the theta, let's turn that into a theta and think about the values that could make sense. I don't know, I'll start with -2 pi, I guess, and then -3 pi over 2. So just I want some negative values. And again, the quadrantal angles are really helpful as far as that goes. I'm kind of out of room, so I'll just stop there. So again, we're going to take the cosine of -2 pi, which is 1. The cosine of -3 pi over 2 is 0. The cosine of -pi is -1. The cosine of -pi over 2 is 0. The cosine of 0 is 1. The cosine of pi over 2 is 0. The cosine of pi is -1, etc. Okay, so we can kind of see how the x is going to oscillate. And then the y value. So basically, we're just going to take the opposite of the cosine of theta, which we can see in our x, and then add 2 to it. So -1 plus 2 is 1. 0 plus 2 is 2. +1 plus 2 is 3. 0 plus 2 is 2, negative 1 plus 2 is 1, 0 plus 2 is 2, negative negative 1, so 1 plus 2 gives me 3, etc. So if I plot those points on the graph, I have 1, 1, 0, 2, negative 1, 3, but then back to 0, 2, back to 1, 1, back to 0, 2, back to negative 1, 3. So notice that's what's happening, is that really it's only that graph on that little piece. And that's what we said here, is that our domain was only going to be from negative 1 to 1, and our range was really from 1 to 3. And we can see that graphically here when we look at our t-table. And as far as how we would have the arrows go, I mean, like they're going in both directions, right? So basically, you would kind of want them to point in both directions because they keep kind of bouncing back and forth between there. So that's what that implies. In this last one here, remember we had that x equals e to the t, and that y was the opposite of that, plus 2. So we can go back to the t's. And again, you're allowed to have negative exponents. So, and I'm just going to substitute the value in the calculator. So like I would just find e to the negative 2 in the calculator, and then do that same thing here. So if I took e to the negative 2, notice that I get about 0.1. And then hopefully you guys would trust me for these other ones. So then what we would do is do the same thing. E to the negative 1 ends up being about 0.4. E to the 0, of course, is 1. E to the 1, of course, is 2.7. And then e to the second is about 7.4. Okay. Now we're going to take the opposite of each of those and add 2. So negative 0.1 plus 2 is 1.9. Negative 0.4 plus 2 is 1.6. Negative 1 plus 2 is 1. Negative 2.7 plus 2 is negative 0.7. This would be negative 5.4. So if we plotted those points, would be 0.1, 1.9, 0.4, 1.6, 1, 1. 2.7, negative 0.7, 1, 2, 3, 4, 5, 6, 7.4, 1, 2, 3, 4, 5, negative 5.4. And we can see that these are going to connect as well. Now, as far as graphing what is going to end up happening, let's think about what we were looking at here. Remember that our domain here is just going to go from 0 to infinity, and the range is negative infinity to 2. So even though the first point we plotted was here, do you see that if we extended, probably what's going to happen is we're going to end up with an open circle at that point 0, 2. And then as we see, this is going to just continue down this way. So I think it's really neat how we can algebraically think about what the domain and range are going to be in each case, and then about how graphically we can see that come to fruition. Okay, so there's one problem like that in the homework on the assignment, I think one, maybe two. On the assignment sheet it says to reference this example. Okay. All right, so one other thing, we have example 6. It says find two different sets of parametric equations for the rectangular equation y equals 5x plus 6. You guys, for something like this, there are lots of possibilities that could happen, that you could have, like an infinite number of possibilities. One real easy thing to do is just make x equal to t, for example. And then your y could just be 5, and then in place of, I should put t, 5t plus 6. So that's a really popular one here, okay? Another possibility could be to do something like x equals, like, pick a trig function, the sine of theta, and then you would have y equals the sine of theta plus 6. So like that's another possibility. So pick a trig function, okay? Something else, like if you want to have a little more fun with it, what you do is you could do something like, all right, let's do x equals t plus 2. So then again, y equals 5x plus 6. Your x was t plus 2. So then you could distribute and you would find that that would be 5t plus 16. So then your set of equations would be that x is t plus 2, y is 5t plus 16. So there are really a ton of different possibilities that you can have. The most popular, and I guess the least amount of work, are if you choose x equals t and then x equals some sort of trig possibility. Okay? All right, moving on. This example 7 asks us to eliminate the parameter for a hyperbola opening horizontally, okay? And we want to make sure that we think about the fact that this is going to be opening horizontally. And again, when we've had these and we've eliminated the parameter, we've isolated the trig function part of it. So if we do that here, we see that I have x minus h over a equals the secant of theta. And then here, y minus k over b equals the tangent of theta. Okay. Once again, we're going to recall our Pythagorean identity involving secant and tangent, that tangent squared theta plus 1 equals secant squared theta. And let's put those in. So for tangent squared theta, I'm going to take y minus k over b squared. And then for secant squared theta, I'm going to take x minus h over a and square it. And again, we're looking to find the parameter for a hyperbola. So I could move this guy over. And we can see that if we write it in a form that is more familiar, that we would end up with that standard form. Whoops, I forgot to square the a. That x minus h squared over a squared minus y minus k squared over b squared equals 1. Which makes sense because this told us that the hyperbola should open horizontally. And here, since the x is our positive term, we know that our axis is going to be coming this way, okay? If your hyperbola opens vertically, then that means that we're going to use these equations instead, that we would use x equals h plus b tangent theta, and that y equals k times a secant theta, okay? So in your homework, they ask you to use work from the prior problems to write parametric equations of conics, like we're going to be doing in example 8. You don't have to memorize those equations, okay? This is just kind of a way to connect what we did with the conics with the parametric equation. So this says to find the parametric equations for a hyperbola with vertices at 0 plus or minus 2 and foci at 0 plus or minus 4. So what this tells us, first of all, based on what we know about our conic sections, is our center. We know our center is at 0, 0. And if we have these vertices at 0 plus or minus 2, this tells us our a value, doesn't it? This tells us that a is 2, and notice that there's movement along the y. And we see that our foci are at 0 plus or minus 4. So this tells us that our c value is 4. And again, of course, that's also affecting the y, which makes sense. So what this tells us is that this is going to be, they told us it was a hyperbola, and it tells us that our transverse axis is going to be along the y. So notice that this opens vertically. And so because we've determined from this information that it opens vertically, what that means is that we're going to want to use these equations to help write our parametric equations. Okay, so in these equations, we need to know H and B and K and A. Well, we know H and K and we know A, but we don't know B. But just like we did before, we can use the relationship at the Pythagorean relationship for hyperbolas, which is that c squared equals a squared plus b squared. And we can see that's going to be 16 equals 4 plus b squared. So that tells us that 12 is b squared, so b is going to be 2 root 3. Now, usually when we were solving for b squared and the other pieces, we left it as b squared, but notice that in these parametric equations that b is just b, so we did have to take the square root in that case. Okay. So if we look at these parametric equations, remember that this is h and k. So this is telling us that x equals, my h is 0 plus b is 2 root 3 tangent theta. And then y equals, my k is 0 and my a is 2 secant theta. Well, obviously we're not going to want to leave the zeros in our answer. So I would just write this as x equals 2 root 3 tangent theta and y equals 2 secant theta. Okay. So again, you won't have to derive the parametric equations. They'll kind of give you that information based on what you do when you write the rectangular equation. So you can kind of work backwards from there. So again, now that we know that this, like in example 7, if these were the parametric equations, that tells us that the hyperbola is going to open horizontally. And so if the hyperbola opens horizontally, those would in turn be the parametric equations that we use. Okay. There is one more example, example 9. I'm going to do a separate video for this one, just because. But so hopefully that gets you guys started on section 9.4b. Okay, thanks. Have a good one.